Hello students, today in this lecture we will discuss about differential indexing. And as we have discussed in our previous lecture, we will also understand what is the difference of this differential indexing method compared to that compound indexing method. So to understand this differential indexing method, let us have a look at simple arrangement that is available in the universal dividing head. Because compared to the universal dividing head available in maybe compound indexing method or maybe in simple or plain indexing method, there is certain changes. So let us understand. As shown in the figure, indexing plate is available. That indexing plate is connected through this crank and crank pin. And this crank and crank pin is directly connected to the worm wheel as the connection shown in the figure. This worm wheel is connected to the worm gear, and this worm gear is connected to the workpiece, which is the simple arrangement which we have discussed in our previous lectures. But in addition to that, in this assembly certain another gears are also available, which you can see. This worm gear is connected to the another gear, and this gear is coupled to another gear train which is shown over here, and this is the main gear train, and this gear train is directly coupled to this indexing plate. So now we have just understood which are the parts available in this differential indexing mechanism. So now how this differential indexing mechanism will operate, we will also understand that. And to understand this, let us take a simple arrangement. First, to rotate the workpiece, now what are the movements are required? So for that, first, rotation of crank pin on the indexing plate rotates the worm wheel. In this rotation of worm wheel rotates the worm gear, and rotation of worm gear in combination rotates the workpiece also, and with the rotation of workpiece there is also gear is connected, and this gear will also rotate, and this gear is connected to the gear train, and the gear available at this gear train, because it is directly coupled to this gear train through this shaft, this another gear will also rotate, and this gear transmits power to the last gear which is directly connected to the indexing plate, and so now this gear will also rotate, and the rotation of this gear is directly applied to this indexing plate, and the rotation of this indexing plate further rotate the workpiece as per the gearing ratio available. So in simple words, if we say the workpiece is rotated by two means, first by simply rotating the crank pin, which will through arrangement also rotate the workpiece, and the another gearing assembly that is also available, which is connected from worm gear to the indexing plate. This will also enable to rotate the workpiece. And how this rotation will be helpful to obtain the any number of gears or any number of division on the workpiece, that we will understand. And as a standard, as one can see, different number of gears needs to be used in this particular assembly, and there are standard number of gears are available to be used in this dividing head. So the standard number of gears available in the dividing heads are, there are 24 number of teeth are available on the gear, and there are two sets are available that are having 24 teeth, and the another gear available that have teeth that are 28, 32, 40, 44, 48, 56, 64, 72, 86 and 100, and all these number you must need to memorize. And in addition to this, in many number of universal dividing head, there are also other gears are available, such as that gears have teeth that are 46, 47, 52, 58, 68, 76 and 84. So these are the different standard gears are available which needs to be adjusted in this dividing head, and how this needs to be adjusted and how these gears or their teeth that needs to be calculated, that we will study in our further topics. Now to understand the example or to process of this differential indexing, we will take a simple example. So suppose if we want to generate 73 number of division on the workpiece using any indexing method. So if you have asked directly this question and they have not mentioned any indexing method, then how you will decide which indexing method needs to be used? So for that, simply let us recall all that indexing method. In first method, that is direct indexing, as we know it is useful up to 24 number of division. So these are more than that, so that cannot be used. Now the second one, that is simple or plain indexing, and that method is valid up to 40 number of holes, and these are also more than this, so that method simple or plain indexing cannot be used. Our third method, that is compound indexing, and as you recall, compound indexing, in this method the first step is to divide the number into its factor. That means compound indexing is useful when the given number can be divided into certain factors. So if you see the number given over here, that is 73, and try to divide this number 73 into exact numbers or in natural numbers. So this 73 cannot be divided into any factors. That means compound indexing method cannot be applied to the numbers which cannot be factorized. So that is the limitation of this compound indexing method. So in such cases, this differential indexing method is used. And to understand this differential indexing method, we will use simple example as we have discussed. What are the steps to be followed to enable 73 divisions on the workpiece using this differential indexing? So for this, our first step is to select nearest number to the given number which can be easily indexed through this simple indexing. So 73 and the nearest number to this 73, if we say, that is the 70, and try to select the number for any of the method or for any of the number given in the differential indexing which has or which is multiple of the 10. So for this 73, the nearest number to 73 in multiple of 10, that is the 70. So the new number that is selected, it is 70. Now next step is use simple equation which is used in the simple indexing. So the equation available in the simple indexing that we know, that is 40 divided by n, and that n is nothing but the number of divisions required on the workpiece. So over here, number of divisions required, that are 70. So that is 40 divided by 70, and if you solve this, you will get the number that is 4 divided by 7. So over here at the end, we will get the answer that is 4 divided by 7. And if we interpret this, the interpretation of 4 divided by 7 is the crank pin needs to be rotated through 4 holes on 7 holes indexing plate. And as we know, in universal dividing head, only brown and sharp standard indexing plates are used. And if you recall, is there any 7 number of holes are available in that indexing plate? No, there is no 7 number of holes are available on that indexing plate. That means we need to convert this fraction form into the possible number which can be obtained on that indexing plate. And for that, we have multiplied this equation by 3. And after multiplying it by 3, you will get the answer as 12 divided by 21. And now if you recall, and always keep it in mind, denominator number must be available in the indexing plate, and over here 21 is selected. Now if you have any confusion that why 21 only selected, so for that just simply try, as the number available is 4 divided by 7. So the denominator that can be adjusted in the multiple of 7 only. So first try 7 into 1, that is 7, but 7 is not available in indexing plate. So second is 7 into 2, that is equal to 14, and that 14 is also not available on the indexing plate. So now next we try, that is 7 into 3, that is 21, and as we know this 21 is available in the indexing plate, and that's why we have selected the number 3. And so at the end the number that we have obtained, that is the fraction form, that is 12 divided by 21. And the interpretation of this number 12 divided by 21, that is for one division to obtain, 12 holes to be rotated through crank pin on the 21 holes indexing plate. And as we want to obtain 73 division, so this process needs to be rotated 73 times. So now as you can see, for 73 division, this index crank is turned 12 holes in 21 hole circle 73 times. And if we obtain final total number of revolution that are obtained after performing these 73 divisions, so we will just simply multiply 73 into 12 divided by 21, because this 12 by 21 revolution we are repeating this process 73 times. So you will get the answer as 876 divided by 21, that is nothing but the 73 into 12 divided by 21. And now try to convert this number into the fraction form, and as you convert in the fraction form you will get the answer, that is 41 and 15 divided by 21. That means to obtain 73 divisions we have given crank total 41 rotation plus 15 extra hole movement on 21 hole circle. And as we know, for one complete revolution of the workpiece there is worm and worm gill arrangement is available, and due to that arrangement 40 revolution of the crank wheel result into one complete revolution of the workpiece. But over here we have given 41 complete revolution, that means we have given extra movement to that workpiece to obtain this 73 division. So it is not possible to obtain equal number of divisions or equal number of teeth on the workpiece. So whatever the extra movement we have given to this workpiece, that needs to be removed, and to remove that we are using that gearing assembly. So first of all let us obtain the value which is the difference from that 40 number. So now as we know, for one complete turn of workpiece, as we have discussed, it should make 40 complete revolution. And so here we have obtained extra movement, and the extra movement that is obtained is, we can just simply obtain it by subtracting it from 40 number. So it is 41 and 15 divided by 21 minus 40. So if you simply solve this, you will get the answer as 36 divided by 21, and try to solve and try to remove as number of factor as possible from this given number, and further factorizing this you will get the final answer as 12 divided by 7. So this is the extra movement that is obtained during this movement. So this needs to be subtracted, and to subtract this movement we will use gearing assembly, and for this we must need to design the gearing arrangement or gearing ratio that is required to subtract this movement. So how one can calculate this gearing ratio? For that let us have a look at another step, and hence the turns of crank are to be lost through the movement of the plate that we have discussed. So the required gearing ratio, that is 12:7, that needs to be subtracted. And as we know, this gearing ratio 12 divided by 7, that means driver gear that has 12 teeth and the driven gear that has 28 teeth. But as we know, this 12 divided by 7 number, so 12 teeth and 7 number of teeth, that gear is not available in dividing head. And for that we need to convert that particular gear head into the available standard gear sets. And for that we have multiplied this particular fraction form with the 4, and multiplication with the 4 will give you final answer as 48 divided by 28. That means driver gear has 48 number of teeth, whereas driven gear has 28 number of teeth, and this driver and driven gear assembly will compensate for this extra movement. And so this is directly obtained by just providing this gearing ratio to this universal dividing head. And for this one must need not to give any extra movement to that crankpin, and this is only automatically accommodated by using these gears. So this is the method to obtain the gearing ratio that is required in the case of differential indexing also, and the arrangement that is required to obtain 73 divisions on the workpiece using this indexing method. So if we just summarize, in this case, first of all, to obtain this 73 number of divisions, the rotation given to the crank pin, that is 12 divided by 7. So this complete rotation needs to be provided, and if you convert this 12 divided by 7 into more fractional form, you will obtain that 1 and 5 divided by 7. That means on 7 hole plate, 1 complete revolution needs to be provided and extra 5 holes to be rotated. And for that particular arrangement, as we have discussed in compound indexing, first select indexing plate which have given number of holes, and after that further provide the rotation. So the interpretation of 12 by 7 that can be obtained from the simple compound indexing method, and the gearing ratio that can be obtained from this extra movement that is obtained from this calculation. And from this, try to convert this gearing ratio on available standard gears, and these are arranged as a driver and driven gear in the universal dividing assembly. So this is simple steps to solve the example given in the case of differential indexing. Now to understand this differential indexing in detail, let us take another example and try to solve it by your side and then compare it over here. So suppose now you have asked us to generate 119 division on the workpiece using an indexing method. So first try to recall which indexing method can be used, and you will come to know that only and only differential indexing method can be used. Now the next step is to select the nearest number, and nearest to 119 in multiple of 10 number available is 120. The next step is to use the equation of simple indexing, and using the equation of this simple indexing, that is 40 divided by n, you will get final answer, that is 6 divided by 18. Now as we know, this 6 divided by 18 indicates that on 18 holes circle, 6 holes to be rotated for 1 complete division, and to obtain 119 division, this method or this process needs to be repeated 119 times, and due to that 119 time repetition, the final total complete revolution that is given by the crank, that is nothing but the 119 into 6 divided by 18 revolution, that will give you 714 divided by 18, and further converting into a partial form, it will give you answer as 39 and 12 divided by 18. And as we know, For one complete turn of workpiece, it should make 40 complete revolution. That means for one complete revolution of the workpiece, crank pin needs to be provided 40 complete revolution. But over here, we are obtaining some of less movement, which you can see from here. So what is the less movement that is obtained? So that is nothing but the difference between exact complete revolution, that is 40, minus the revolution obtained, and that will give you the answer as 6 divided by 18. So this 6 divided by 18, that is the less movement obtained. And now we need to design the gears which will provide this extra movement, that is 6 divided by 18. And so for that, simply use the gearing ratio arrangement, and as the required gearing ratio, that is 6 divided by 18, which is needs to be provided by this gearing arrangement. So from 6 divided by 18, if you solve, you will get 1 divided by 3. So the meaning of 1 divided by 3 is 1, that means driver gear has 1 teeth and driven gear has 3 teeth, but this number of or this type of gears are not available. So we need to obtain in this particular ratio the standard gears available, and for that we have multiplied numerator and denominator by 24, because 24 number of sets are available as we have discussed in this lecture. So the final gearing ratio that is obtained is 24 divided by 72, as shown over here. So this 24 divided by 72 will interpret nothing but the driver gear has 24 teeth, whereas driven gear has 72 teeth. And as the movement obtained is less, we need to provide extra movement. Means if we are rotating the crank in clockwise direction, then this gearing ratio has to be adjusted such that the extra movement that is provided is also in the clockwise direction. And if the extra movement is given, then we must need to provide, or we must need to subtract that extra movement. And in such that type of cases, if crank is rotated in clockwise direction, then the gearing arrangement is such that it provides the rotation in anti-clockwise direction, so it will compensate that extra movement. So over here, this required gearing ratio is 24 by 72. So in examination, after following this certain number of steps, you must need to give interpretation of the crank pin rotation required, the gearing ratio that is provided, and the final number of division that is obtained, that we have discussed. So this is the differential indexing method, and we have discussed two variable examples to let you familiarize with the different variation that can be asked in this differential indexing method. So I hope it is clear to you about these different indexing methods that we have discussed, that is direct indexing, simple or plain indexing, compound indexing, and differential indexing method. And these all methods are much and more important as an examination point of view also, and this calculation will also be helpful during practical time. So practice all that example, practice different examples also, so that it is easy to you to solve these examples during examination. So looking forward to see you all in our next lecture. Up to then, thank you.